We're ready. All right, today 11-4, super boring day by the way, so we're jazzing it up with a little webcam action. Okay. Um, so talking about compound events today and exclusive, mutually exclusive and inclusive, and calculating those types of probabilities connected with those events. So this is where we left off on 11-2, talking about what it means when you have and or as you're calculating probabilities. And when you see and, that's going to indicate when you multiply, and or is going to be indicating that you add. So if we calculate some probabilities here, dealing with cards, let's say we have the probability of choosing one card, and that card is a 5 or a king. So how many cards are a 5 or a king? 8, right? 5, 4, and 4. Okay. And if we calculate those probabilities together, or separately, we have 4. Well, it's a weird 4. 4 50 seconds plus the other 4, because it says or, so it could be either card would be a favorable outcome. So 4 50 seconds plus 4 50 seconds is a total of 8 favorable outcomes out of the 52 possible. Okay, which then that reduces, divide by 4 to 2/13. Okay, so there is a situation where we have or, like 5 or a king. There's more. It's all together. Favorable outcome would be a 5 or a king, so you have to add them all together. In B, it says a face card or a 2, so same situation there. How many face cards do we have? 12 total. And how many 2s? 4. And then none of them are the same, right? There's no face cards that are 2s, so we're good there. So if you add 12 and 4 together, you're going to get 16 total favorable outcomes out of the 52 total, which that would simplify, divide by 4, you'd get 4/13. 4/13. Okay, same thing, choose a red 4 or a prime. Prime was kind of weird with cards, but I guess it would be, a prime would be, well, a red 4, there's 2 of those. Prime number, we could say, would be like, one's not prime, but 2, 3, 5, 7. So there's 4 times 3 or 12. Wait, 4 times 4 or 16 primes. So I guess let's just call that 18. But same concept. 18, which is the same as 9/26. Okay. All right, moving on. So and, when it's and, you multiply. When it's or, you add. So be careful when it says or. You're going to have probably more outcomes than you think. Alrighty. Continuity error. How do I get over here now? So we have this concept of mutually exclusive events, and this happens when we're talking about a compound event, so made up of more than one simple event. So let's just say we're talking about event A happening and B happening, and sometimes when you're talking about two different things, they can have outcomes that they would share in common, or they might not share any. So if they don't share any of the outcomes, right? So I guess you could say, whatever their definition, mutually exclusive events are events that cannot both occur in the same trial. For example, they give rolling a 1 and rolling a 2 on the same dice. You can't do that, right? It either has to be a 1 or a 2, so it's not like they're shared. So I think you'll get a feel for mutually exclusive as we look at some examples, but if you're drawing a Venn diagram, that would mean that those two events do not have any overlap. You might also see this drawn like this. So if we did have another Venn diagram drawn, and we just generically draw it like that, and let's say we had, this would be like dogs and, I don't know, pets or something. And then sometimes dogs can be pets, right? I like your cats thing. Let's go back to cats. Dogs and cats. So if it was dogs and cats, would there be any overlap between the dogs and cats? Yeah, the dats, right? The cogs. Have you ever seen Spaceballs? Yeah, like Barf. He was kind of a part something, wasn't he? Anyway, so this would be empty. Maybe there was like 13 dogs and 20 cats, and no cat was a dog. So you would have an empty overlap there that would be mutually exclusive. There's nothing in common. Anyhow, if they're mutually exclusive events and you're calculating probabilities, then the probability of event A plus the probability of event B would be the probability of A or B together. So you just add those two probabilities together. Here's an example. Group of students is donating blood during a blood drive. Student has a 9/20th probability of having type O blood and 2/5 probability of having type A. Why are the events type O and type A mutually exclusive? You can't have both, right? Can't be both. One or the other. So type O and type A, I don't think you can have type OA. So you can't be both, so it's either one or the other. So the probability that a student has type O or type A would be just the sum of those two individually. So type O was 9/20 and type A was 2/5. So 9/20 plus 2/5. How do you add fractions? Common denominator, so we got to multiply, so that's going to be 8/20. So the chance of them in this situation having type O or type A would be a total of 17/20, which what is that as a percent? What is that as a percent? 85, good. 85%, nice job. All right. Okay, next page. Each student casts one vote for senior class officer president. Of the students, 25 voted for Hunt, 20 for Klein, and 55 for Villa. A student for the senior class is selected at random. Explain why the events voted for Hunt, Klein, or Villa are mutually exclusive. Only can vote for one. Good. Only can vote for one. Okay. So because you can only vote for one, those events are mutually exclusive. So you didn't vote for two. And the probability a student voted for Klein or Villa is going to be 20% plus 55%, which is a total of 75%. So you can just add them together. Good. All right, not much action. Let's get into some action here now. Let's talk about what happens when they are inclusive. Now this is a little bit more dangerous, it's a little scary now, okay? We could actually screw this up. We could double count. We don't want to screw this up. So inclusive events are events that have one or more outcomes in common. When you roll a number cube, the outcomes rolling an even number and rolling a prime number. Okay, there's one prime number that's even too, so you got to be careful there. This is where good old John Venn and the Venn diagram comes in handy when you are trying to calculate these probabilities. Okay, so this is a Venn diagram. You've seen these before. If you draw a picture, it can help you not mess up and double count the ones that are in both. So inclusive events are events that can happen at the same time, and the probability of two inclusive events, A or B, happening is going to be the probability of A plus B minus, and this is the tricky part, you have to subtract out the intersection because you can't double count it. So be careful not to double count. All right, so I'll show you how we handle this. Find the probability of a number cube rolling a 4 or an even number. Okay, well, rolling a 4 or an even number, are those inclusive? Yes, they are. So those are inclusive. And so we have to be careful to not count something twice. So let's draw a little picture and just see what the picture looks like. So if we draw a little picture here, and we make a little Venn diagram, we put a little Venn diagram in there, and we say probability of rolling a 4 or an even. So here's a rolling a 4, here's an even. Are there any 4s that are even? It's just 4, yeah. So the 4 goes in the middle there, and the rest of the evens, 2 and 6, go right there. So how many of the outcomes are 4 or even? 3, 4, 2, 4, or 6. All right, so right there you draw the picture, you can see all of those values inside the Venn diagram are going to be our favorable outcomes. 3 out of 6 or 1/2. Nice, Mr. Eckhoff made it today. Hold on, we got to get you on camera. No. See him back there? All right. We're just recording. Hi. What happened? Uh-oh. All right, we're back. So rolling an odd number or a number greater than, oh no, we're still on this one. I'm going to show you what this looks like if you just calculate the probabilities separately. So let's say the probability of 4 or even is going to be, since it's inclusive, the probability of 4 plus the probability of even. And then since they're inclusive, you have to do minus the probability of 4 and even. Okay, so probability of 4 is going to be 1/6. Probability of even is 3/6 minus the probability of even and 4 is that 1/6 again. So you'll see 1/6 plus 3/6 minus 1/6 gives you still 3/6. So it does feel a little redundant, especially when you can just, if you make the picture and just look and say, oh, there they are, 1, 2, 3, 4. I mean, 1, 2, 3. Can't count to 4 through 3. It's Friday. Yeah. Okay. Rolling an odd number or a number greater than 2. All right, so rolling an odd number or a number greater than 2. Again, if you draw the picture, then you don't have to worry about doing all that other stuff. Okay, sometimes it's just good to draw the picture. So odd number, so an odd or a number greater than 2. Well, what is the intersection or the overlap of a number greater than 2 and an odd? That's going to be 5. Is that it? What about 3? 3 as well. So 3 and 5 are in the middle. Just a dice. And then the other odd is 1. And the numbers greater than 2 that aren't 3 or 5 are going to be 4 or 6. So how many possible numbers are odd or greater than 2? 1, 2, 3, 4, 5 out of 6. So 5, 6. Right? If you were to follow the rule, you'd say probability of odd plus probability of greater than 2 minus probability of the both, odd and greater than 2. Right? So the probability of odd would be 3, 6. Probability of greater than 2 is 4, 6. Right now you already see 7, 6. I can't have a probability more than 1. Something's wrong here. And what's wrong is you're double counting 3 and 5. So you have to make sure you subtract the, I should have made that a 2. You have to subtract the 2 possible outcomes when it's both. So anyway, final answer here, ka-chow, 5 out of 6. You don't have to draw the Venn diagram. You could do what I'm doing in blue. You could write the rule out like that as well. So it's just whatever. It's kind of a preference thing. Personally, I like to have the picture, but question. If you can make the diagram and figure it out, then that's fine by me. I mean, unless I explicitly have like the rule written out and I want you to show how it works. But all right. Card is drawn from a deck of 52. Find the probability of Drawing a king or a heart. Is this inclusive or mutually exclusive? King or a heart? Can it be both? Yeah, so that's inclusive. Okay, so if it's inclusive, I'm just going to draw a little picture. All the kings, all the hearts. Aw. Any kings that are hearts? Should be one king of hearts, right? 3 kings that aren't hearts, and 12 hearts that aren't kings. Haha, the probability of drawing a king or a heart is 16 out of 52, which is 4 out of 13. That would be how you do it when you draw the picture. If you're doing the probability, you'd be probability of heart plus probability of king minus probability of heart and king. So heart would be, what is it? 1350 seconds. Geez, that is a crusty. 1350 seconds plus 450 seconds minus 150 second, which gets me to 1650 seconds, yada, 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 same thing. All right, yep, that's right. Drawing a red card or a face card. All right, red card or face card. Red card, face card. All right, let's let you guys see if you can come up with the right answer here. I'll give you guys a try. I'll pause it. All right, let's find out if you got it right. So drawing a red card. How many red cards are there? There are 26, right? And a face card. There's 12 face cards. How many face cards are red cards? 6. That means there's 20 red cards that are not face cards. And there's also 6 face cards that are not red cards. So that's what my Venn diagram looks like. And then if I want to know the probability of either red card or face card, I just add all those up and get 32 out of 52. So 32 out of 52, that's going to be what, 8 out of 13. Yeah. And I guess technically you also should have, if you're making great Venn diagrams, that's 32, so then the other 20 would be like outside of there, like that. But, all right. Ooh, the colorblind question. 3,510 drivers surveyed, 1,950 were male, 103 were colorblind, only 6 of the colorblind were female. So, this one's good for a Venn diagram. Go CB for colorblind, M for male. Of the 103 colorblind, only 6 were female, so that means the other 97 were male. So there's 97 male colorblind, and there's 6 that are female. And then of all the males that were surveyed, 97 are colorblind, so that means 1,853 are not. So I think that counts for all the colorblind, male or not male, or so this would be colorblind or male. Sum of all 3 of those is 1950 plus what, 100 plus 6, so 1,956 out of a total 3,510. Right, so I don't know. Personally, I like to just draw the picture and have the picture up there. 55.7%. Yes. Yeah, I think fraction probably the best, just because if sometimes it's like, let's say it was like 6 out of like 3,510 and you rounded it to like 0.001. Someone else could do it wrong but still get 0.001 because it's such a small number. So I think the best is just simplest form fraction, which if you're using these calculators, it does it for you anyway. Unless I say like put it as a percent or something. I think percent probably most people understand better, but for math teacher and grading, fraction's the best. Okay, this last one, let's just decide mutually exclusive, yes or no, and we'll be done. Probability of a 10 or a diamond. Is this inclusive or mutually exclusive? Can it be both? So it can be both, so that would be inclusive. There is a 10 that is a diamond. Probability of an ace or an 8. Those cannot both be, can't be an ace and an 8, right? So those would be mutually exclusive. And the last one, spade or a number less than 6. That you definitely have some overlap there, so that would be inclusive. All right, so high five, happy Friday. Get your shovels and your snow blowers ready because we're going to get another big snowstorm tomorrow. Aren't you excited? Yeah. All right, thanks. Bye. Bye. Wow.